Well, thanks a lot, Dominic, and the ICCS team for inviting me to give this talk. I'm representing the M Squared Lines project. Really, I'm not going to be talking that much about the M Squared Lines science. I'm more going to be talking about some approaches to data and software and computing that I think have some broad relevance across this this collaboration, and which also happen to be my sort of obsession / passion. Hope you find this material interesting and get something out of it, and I'll look forward to some discussion at the end. First, let me just talk a little bit about the central problem that M Squared Lines aims to address. M Squared Lines, by the way, stands for Multi-Scale Machine Learning in Earth System Modeling. For decades, really, climate models have shown persistent biases in sea surface temperature that won't go away. And these biases really, limit our ability to make confident predictions about a lot of future things in the climate system, because ultimately SSTs and air-sea interaction drive many of the teleconnections that control, large-scale weather patterns that ultimately are driving changes in drought and flood and heat waves and all of the extreme events that we care about. So our project sort of takes the view that really this is a core thing that climate models need to do better. And we start from the hypothesis that these biases exist through poor or lacking representation of key physical processes, which is ultimately due to the relatively low resolution and numerical limitations of climate models. So the vision for M Squared Lines is to improve the skill at surface ocean, ice, and atmospheric fields on timescales of hours to centuries in global climate models, and provide more reliable climate predictions through the development of new machine learning, data-driven, physics-aware parameterization of subgrid ocean, ice, and atmosphere processes. And the goal is that these new subgrid parameterizations will reduce the structural model biases in existing climate models. Particularly, we're working particularly close on the GFDL climate model, but also collaborating with NCAR and IPSL. And so the process is, starting from high resolution models, which do a lot better with many of these biases, but are much more expensive to run, and also observations, and also starting from data assimilation products to develop new physics-aware and interpretable subgrid machine learning models, use these and actually implement them into climate models, and through evaluation, calibration, tuning, obtain more skillful climate models. So, this is a really kind of exciting opportunity, right? By tackling not one sort of specific element of the climate system, but really looking at, the three main physical components, atmosphere, ocean, and ice, we're searching for an opportunity to identify, universal machine learning methods and insights that cross disciplines. So here I've got just a bunch of the sort of different types of processes and physics that we're thinking about. Our team involves scientists from a lot of different disciplines: oceanography, atmospheric science, experts in data assimilation and cryosphere, and also machine learning scientists who, before we started this, had virtually no exposure to climate modeling and the data and the type of approaches we use. And so this is a really exciting opportunity to bring these people together. But there's also some real risks in a broad approach like this, right? So there's a lot of barriers to collaboration that exist when you try to bring together a team like this. One of the most obvious ones is sort of jargon and the lack of shared terminology and scientific understanding, limited overlap in scientific expertise. And we've tried to tackle these through really deliberate sort of educational efforts to learn each other's languages. But there's also a lot of data and software related challenges. And that's what I'm going to sort of be focusing on today and talk about some of the approaches we've used to try to confront some of those challenges. Around data, it's really difficult to share these large complex data sets associated with the processes we're interested in studying, whether it's clouds in the atmosphere or eddies in the ocean. And there's a lot of challenges also in software, right? The work we're doing is complex. It's hard to just easily share code. It's hard to generalize methods. There's a lot of difficult pre-processing and analysis steps that have to happen here that aren't necessarily machine learning per se, but that are consuming a lot of time and effort. So I'm going to talk about, my talk is kind of in two parts, focusing in part one on sort of the data infrastructure and the approach to infrastructure that we have taken, and part two on the software. Now, in both of these, we are working very closely with the Pangeo community, which has been sort of confronting these problems in a general way for several years. And so I'm gonna now tell you a little bit about what Pangeo is. It's a project that I'm very passionate about and have sort of focused my whole career on recently. And apologies, I'm sort of switching themes between slides because I shuffled together slides I have about M² lines and Pangeo. So hope you don't mind sort of a little visual clashing as we go forward. But really, these projects are closely intertwined at this point. So what is Pangeo, first of all? So Pangeo is an open science community focused on big data geoscience. It was founded at Columbia in 2016, and it's really a sort of grassroots collaboration between scientists and software developers around open source tools for solving, real problems that we have in data intensive research. And by grassroots, I mean that it existed pre-funding. It was just people who came together who wanted to work together to, get stuff done. It was originally a collaboration between folks at Columbia and NCAR, and we got some funding from the NSF, from NASA, and from the Gordon and Betty Moore Foundation. And the project has really grown to include a lot of partners around the world, and we strive to make this a really open and inclusive community. So, consider this an invitation to join the Pangeo community. So what do we do? What does Pangeo do? How do we operate? Well, it's really sort of a continuous loop of development and iteration, right? We're always starting from scientific users and use cases who are bringing science questions and challenges that they're facing around answering those science questions with the tools available. So in 2016, it was very much, about, big data. We had petabytes of data to process. And the tools we had available to us were not really cutting it. Today, there's a lot of focus on machine learning and integrating data with machine learning. And what our community does is we seek to make contributions in open source software, really broadly defined, that are going to help unblock those use cases and make the science move faster. And we're less likely to create new tools and more enthusiastic about contributing to existing ones and making them integrate and interoperate better with each other. And then we deploy these tools, these software environments, on a lot of different infrastructure options. So, HPC centers like NCAR Cheyenne Computer, and increasingly the commercial cloud, where we find we can be very productive. And this process just iterates and has gone on for many years and will continue into the future and evolve. So let me start by talking about the infrastructure piece of this, right? And really, for infrastructure, we're very motivated, both in M² lines and Pangeo, by this vision of open science, right? And so open science is a term that has a lot of different dimensions, but I like to try and sum it up in pseudocode. We'd like to allow everyone in the world to verify and extend all scientific knowledge easily, right? We want to make it accessible to for anyone to do that. And this would be absolutely transformative for society by allowing all of humanity to participate in and build on scientific discovery. So that's a very grand ambition. Just getting a little bit more practical. Okay, can we at least do this within M squared lines? We've got half a dozen different universities and labs involved. We've got about 30 or 40 scientists involved in one way or another. And we've got a couple different scientific domains, right? So at least across our project, can we share projects effectively, share data and code, learn from each other, and work in a more open and collaborative way. And it's hard, but we're learning a lot in the process. So a good place to start is to ask, what's really needed to reproduce and share a scientific discovery? And I like to think about three different elements here. We have the code, right? All the work we're doing here is ultimately driven by computation and analysis of one sort or another. There's the environment that code ran in. So it's not enough to just share the code. We need to know, okay, what versions of software were being used, what libraries were installed on the system. And of course, we need the data, right? We're operating on data, and so we need access to that data. And I think we're in a pretty good place overall regarding reproducibility in science, say compared to 10 years ago. We have a lot of great tools for sharing code. A lot of people now use Git and GitHub and things like that. We have a lot of options for sharing environments, computational environments, from publishing software packages to using Docker, things like that. And those practices are starting to become more used in science. And then, of course, for data, we have fair data, findable, accessible, interoperable, and reusable. And we have a lot of great data repositories like Zenodo or Figshare or Dataverse that allow us to deposit data. And so, we have a lot of the building blocks, I think, that are needed to make scientific data reproducible, except when it comes to what I call data-intensive science. And so when we're talking about weather, climate, and geospatial work, our data are really big. As an oceanographer, I work with ocean model data sets whose size is measured in petabytes. And this term data-intensive science, I use it to refer to just the process of boiling down these very large data sets into some actual insights or understanding or predictions. And machine learning is one way to do that. And there's a lot of other analysis methods that can be used to do that. And so I can't just upload these data to Zenodo, right? Like I can't just put them on my personal website or something to share these data. So we're not quite there yet with for open science in data-intensive science. And this is a problem we're facing in M squared lines and in the Pangeo project more broadly. So the standard sort of way we operate, in science is through what I like to call the download model. This is how I was trained as a scientist. If you need some data, you go download it, right? And you get it on your computer and then you analyze it. And that works just fine for measuring when you're measuring your data in megabytes and gigabytes even. A lot of us now are in the terabyte range where, downloading terabytes of data to your computer can be pretty painful. And as we move into sort of this petabyte range, it becomes impossible to work this way. So what do we do? In response, well, the status quo is to create what I call a data fortress. Okay, so a data fortress, for example, I'm at Columbia University in New York, where we've got a lot of infrastructure to support research. We're very privileged, so we download a bunch of data from wherever it may happen to live out there, and we put it on a supercomputer in our basement. And great, we've got an analysis platform that our scientists can use. And a lot of productive research happens this way. I imagine folks out in the audience there are familiar with this way of working. By the way, please interrupt me if you have any questions or objections to what I'm saying. giving these remote talks, it can be a little impersonal. So I would very much appreciate if anyone wants to do that. Otherwise, we can talk at the end. So this is how a lot of us work today. And have you ever gotten some code from someone that looks kind of like this, right? The problem with this data fortress is that, it works great, if you're inside the fortress, but you're depending on this sort of files and this data collection that's been created there that's not accessible outside of the data fortress, right? And so you can share code all day, but if it's pointing at data that is not accessible, you can't actually reproduce anyone's results here. And so this is a problem even just within M-squared lines, because we've got Columbia, we've got Princeton, we've got NYU, MIT, NCAR. Every one of these institutions has their different computer, their different data fortress, and we can't collaborate this way, right? And so just sort of homing in on some of the general problems I see with the status quo here is that, first of all, the emphasis on files as a medium of exchange is creating a lot of work for individual scientists, downloading, organizing, and cleaning data, setting them up. And these file-based data sets can be a real mess, even if you're dealing with simulation output. So this hard work of data wrangling is rarely collaborative, and the outputs are not reusable and can't really be shared, even though they're very time-consuming. Even doing this type of work, working with many terabytes or petabytes of data, is really expensive. It requires either local infrastructure or access to a big agency supercomputer, and that really limits participation in this type of research. So people from the developing world usually have neither and are excluded from this type of work as a result. And finally, the idea that this data intensive science is happening inside a data fortress really limits access to outsiders. And that's a feature, not a bug. The mandate of those computing centers is to prevent access by outsiders. But when we're trying to encourage collaboration and reproducibility and interaction between teams and projects, that's the opposite of what we want. So what would we like instead? What would we like instead of a data fortress? Well, I like this term coined by Fernando Perez of a data watering hole. We've got these big data sets. Let's all go to the data and use that as a place for collaboration, developing new ideas, and including more people in the scientific process, right? So can we move from a data fortress to a data watering hole? And this is where we're very excited about sort of commercial cloud computing, because the commercial cloud or cloud-like infrastructure operated by, doesn't have to be operated by a commercial company, but mostly is today, provides a different model for how you can interact with data, a public square where everyone can gather, right? And so when we think about this new mode, what we really want is a cloud native approach to working with scientific data. And we've identified sort of three main pillars of what this sort of cloud native scientific workflow would look like. We start from analysis ready cloud optimized data, and I'll dig into what this means a little bit more. But really we want to think about databases, not just files, right? We want to think about okay, what is the actual data set we want to organize, we want to work with at a high level, not about how many files is it split up into on a on an FTP server or something like that. Then we want to bring data proximate computing near that data. We have all these great open source programming environments that can easily be brought close to the data rather than downloading the data to our own computers. And then when we're dealing with big data, we want to be able to leverage elastic distributed processing. So if we have to quickly process a lot of data, we should be able to scale up, do what we need to do, and scale back down. So these are some of the elements of what we call cloud native scientific data analytics. Now, let me dig in. Oh, and we wrote about this in this paper that we call Cloud Native Repositories for Big Scientific Data, if anyone wants to sort of dig into that concept a little bit more. So I'll just spend a little bit of time on this concept that I think is very important, called analysis-ready cloud-optimized data. So first of all, what is analysis-ready data? Right? We really want to be thinking in terms of data sets, not data files. And this is really important in this sort of machine learning research, where we want to reach out to collaborators in other fields who may not be familiar with our obscure data formats. They may not know what a netcdf file is or a grib file. We want to provide really convenient access where all the tedious homogenization and cleaning and alignment steps have already been performed, and that data are curated and cataloged and accessible to computation. So that's sort of the gold standard. And it's well known that across data science scientists spend most of their time preparing data for analysis rather than actually doing their work. So can we do that once and then share those results of that clean data across projects? This is kind of what analysis-ready data looks like. This is an XARRAY data set, which I'll talk more about soon. And it's just in a representation of a data set where we have all our variables together, all of our metadata together, all of our data has been sort of grouped into one analysis-ready object. Then this cloud optimized part is a bit of a technical detail, but it's very important working in the cloud. Traditional file formats don't necessarily work well in a cloud context where we're talking to object storage. And so we think it's very important to use some of these newer formats that support intelligent subsetting, lazy access to data over HTTP connections. Probably getting too much into the weeds. So let me just jump to what is the open science platform that we're using today in M² lines? Well, we've partnered with an organization called 2I2C, the International Interactive Computing Collaboration, which is a nonprofit organization that deploys and operates open source cloud-based infrastructure for the research and education community. So you can think of this kind of like an open source version of Google Colab. We've got a Jupyter hub running in the cloud where we have our data science environments. And then we've got a lot of tools that can interoperate with that, storing code on GitHub, sharing examples, sharing environments through Docker, things like that. And then we've got our data. And for data, we're working with another sort of interesting novel organization called OPENSTORAGENETWORK that deploys their cloud storage outside of the commercial cloud. So our data are living in this sort of cloud-like storage, but not actually within sort of Amazon or Google's cloud. And we're really excited about this platform. We've kind of just got it up and running, but we really think it's going to facilitate some great collaborations across the team. The vision here is that this model is highly extensible. So we have this platform for us, but our data are publicly accessible over the internet. And so, we'd like to see a world in which there are a lot of sort of these different sort of computing sites for projects, maybe some of them in HPC centers, some on the cloud, some in between, a lot of data that's interoperable with this framework. We could really build a federated network of computing and data sites for collaborative research. So that's sort of a long-term vision. Okay, so that concludes the part on infrastructure. Now, what about software? What is the actual software running in this infrastructure? Well, here I'll give a quick overview of what we sometimes call the Pangeo stack, right? So Pangeo community was really emerged out of this idea that we need better tools for working with big data. So we tend to talk about three sort of foundational elements for that stack. When we're in the cloud, we are storing data in the zarr format, which is a cloud optimized storage format for multi-dimensional arrays. You can think of it as similar to HDF5. And in fact, the latest versions of netcdf, of the netcdf library, actually can store data in zarr. So you might as well put netcdf down there at the bottom. Now, on top of that, we've got we sometimes use Dask, a parallel computing framework that allows us to distribute our computations or calculations over many nodes. That's not always necessary, but it can be very helpful. And then kind of at the top of the stack, we have a library called XARRAY that I'll say a few more words about. That is really kind of the core tool we are using to interact with data. And then on top of XARRAY, we're starting to develop a range of more domain-specific packages that do certain important tasks that we need in our workflows, but then don't have to reinvent the wheel in terms of all the other basic layers. And so I'm going to talk about 3 packages that we've been working on: XGCM, GCM filters, and XBATCHER. And XBATCHER, to give you a little preview, is really designed to bridge the gap between XARRAY and the machine learning software world. So let me just first say a few words about XARRAY. So this is a project that's near and dear to my heart. I'm a sort of core developer of this project, and it's been around for 5 or 6 years. It really allows you to do label-based indexing and arithmetic on data sets, right? So it provides this higher level data model than just working with raw arrays. It provides interoperability with the core scientific Python packages, pandas, NumPy, Matplotlib, and it allows you, collaborating with Dask to do out-of-core computation. So if you have data sets that are larger than the memory on your system, or you have a big HPC cluster, cloud cluster, it allows you to take advantage of those computing resources. It reads and writes all of the major formats that are used in geoscience research: NetCDF, HDF, zarr, geotip, GRIB, basically anything you would encounter. And it has some sort of advanced multi-dimensional data manipulation tools, things like group by and resampling and things like that. So we think of it just kind of a Swiss Army knife of general purpose high-level computations on the type of data that we work with in geosciences. Now, the goal of the XBATCHER project is to bridge the gap between XARRAY, which we usually use to open our data, and the various sort of tensor machine learning libraries, right? And so the idea here is that deep learning libraries want to see their data in batches, right? So if you've ever trained a deep learning model, you need to configure your batch size and feed data through it in batches. And so XBATCHER allows us to define a schema that explains how to split a large data set into these batches using XARRAY semantics. It handles things like shuffling, sampling, caching of data, etc. And we're working on now is providing data loaders for PyTorch and TensorFlow to really stream data directly from storage through XARRAY, potentially post-processing it along the way, and into our machine learning pipeline. So what that looks like in code, right, is that we could just open up a data set with XARRAY, maybe do some pre-processing to prepare training data, create one of these batch generators, and then just loop through that batch generator. And here what we're saying is, okay, let's take this data set, potentially many dimensions, split it up into chunks of 10 elements in the time dimension, and use those as our batches for either inference or training in a machine learning model. That's one tool that I kind of just wanted to advertise that I think could be broadly useful within this community, anyone who's working on machine learning in Python. Another challenge that we have tried to confront in our project, both Pangeo and M² lines, is the idea that, the data we're working with, we're talking about working with GCMs. So we really have to think about this idea of a grid cell, right? It's not enough to just have like a big, array of data. Our data really live on one of these finite volume grids. And I imagine folks in the audience are familiar with this, right? So our tracer field would usually be located at the cell center, something like temperature and pressure. Vectors are located on cell faces, so velocity, heat flux, etc. And then other quantities like vorticity might be located at the corner points, right? These are important numerical considerations that you have to keep in mind when you're working with GCMs. And most of our fundamental operations within finite volume GCMs can be understood in terms of manipulations on these finite volume grids. So, I've listed here an example of like what it means to calculate vorticity. What's the sort of finite volume version of vorticity? And, these are really fundamental operators that we need to deal with GCM data. Here, just for fun, I put up what the governing primitive equations look like in this type of notation, right? And so this is what we have to do in a model, but most of our tools don't have any awareness of these grid cells in this way. XARRAY in particular doesn't understand the notion of a grid cell and grid cell geometry. So it's very useful for opening up and loading data sets, but it has some limitations in its data model. And so that's what XGCM is designed to address. So the XGCM package provide some additional higher level concepts on top of these data sets, defining the idea of an axis, right? So we can have, it's really a group of dimensions that lie along the same axis of a locally orthogonal coordinate system. So we can have variables that live at the center of an axis, the left, the right, the inner or the outer position. And using that, we can sort of build up this whole grid object that we can use to describe operations that operate on these grids in a high level. So as an example of that, this is what XGCM code looks to define that C-grid vorticity formula, right? So to calculate vorticity on one of these grids, you have to sort of be aware that the different variables that are inputs to this calculation live at different points of a finite volume cell. So XGCM allows you to annotate a function that's purely numerical. Here in this case is vorticity function, and then explain, okay, what are these different variables? How do they, where are they located with respect to the cell geometry, and then enforce that the inputs and the outputs have the proper coordinates and dimensions. And that really helps simplify the code and avoid a lot of potential errors that can arise when you're writing up these type of operations. Now, how does this relate to machine learning? Well, our long-term goal here is that in M-squared lines, we're developing essentially physics-informed machine learning trained subgrid scale models to replace, the traditional numerical elements of a GCM. And those subgrid models are going to have to operate on the same sort of staggered finite volume grids. And so we want to be able to annotate those models, and we say, okay, here's a model for subgrid forcing. It takes, the velocities at the cell face, the tracer values at the cell center, maybe some other quantities related to the geometry, and it produces an output that's located where? At the cell center, right? We want to be able to mark up and annotate a machine learning model, which will then make it shareable, across different projects, and ultimately, I believe, help with implementing these models into the actual GCMs by creating a sort of language to describe what they do. That's a long-term goal, but it's something I'm excited about, and we're very happy to be working with the folks at Cambridge on this. Dominic's team has gotten involved a little bit in XGCM. Final package that I want to sort of plug here is GCM filters, right? So a big need that we have in this type of work is to filter out and assess the impacts of different scales. In M-squared lines, we are working with high resolution numerical models and trying to diagnose from them what are the subgrid scale tendencies that then we need to parameterize in low resolution models. And so in order to do that, you need to be able to accurately filter out the small scales. This is sometimes called coarse graining. And M-squared lines, in collaboration with the NOAA NSF climate process team on ocean eddies, has developed this new framework and Python package for doing this. And so this started from a theoretical framework developed by Ian Grooms that constructs these smoothing operators based on the discrete Laplacian operator. By framing this around the Laplacian, we can really build filters that understand GCM grid geometry and topology. Just have to be able to calculate the Laplacian. And then we can apply all kinds of different filtering from that. So we've encoded this into an open source Python package that uses XARRAY as a core data model. It can run on GPUs. It can scale out with Dask. And the lead developer of this effort is Nora Luce from CU Boulder, who's done an incredible amount of work here. So just to explain exactly what this does, right, here's an example. Say we want to smooth out scales below 100 kilometers on a pop model with a tripolar grid geometry, one of these nasty custom grids that we find in climate science. GCM filters allows us to define a filter on that space. In this case, we're using a Gaussian filter with a scale of 100 kilometers. The package understands this geometry, right? This grid type, tripolar pop grid with land boundaries. We specify some grid variables that describe, the geometry of the grid, and then we can simply apply this filter to a field to obtain the correctly smoothed version. So this has been really useful in our project. Okay, so I think I'm approaching the end of my time here. So I'll just kind of wrap up and summarize. I know this has been kind of a whirlwind tour of a lot of different ideas and concepts. Just to sum up what I guess I'm trying to communicate is that we really think that open science practices can enhance collaboration and enable new cross-disciplinary discoveries. And I think that's important for everyone operating in this sort of machine learning, intersection of machine learning and physics. For data-intensive science, I think infrastructure is very important for collaboration. And so two key principles that we've tried to advance in terms of infrastructure is this idea of ARCO data, analysis-ready, cloud-optimized data, that really lowers the barrier for collaborators to come in and access and start working with data. And the other is data proximate computing, which eliminates that need to move these big data sets around. And then finally, on the software side, the Pangeo software ecosystem offers a range of tools that are useful for physics-informed machine learning. And I really encourage this community, if you're interested, please, reach out and engage with these projects if you think they might be able to help what you're working on. We're always looking for new contributors. And I'll just kind of close with like a little bit of information if you want to learn more about the Pangeo community. We have a lot of sort of open channels of communication online, and we're perhaps the last community out there that doesn't use Slack, but we really like to try and keep the communication open and have a lot of resources that people can discover on their own and interact with us. So I guess I'll leave out my summary slide and I'll stop there, and maybe there's a few questions or discussion points people would like to dive into. Anybody out there?
Yes, we're just moving around. I'm going to switch the view so you should be able to see. Can you see that all right? Can you see us?
Yeah, I see you all. Yeah, I'm going to stop sharing here and great. Yes.
One part of the room at least.
So
I see a gorgeous purple seats in your auditorium.
That's right.
So Ryan, I've got a couple of questions about infrastructure. First one is on the open storage network. So it's interesting that it's on the public cloud, and I think I can understand why, having seen what public cloud charges for data storage. So what's the financial model? How is this going to, if we put a large data set on the open storage network, how sure are we this can be there in 2 years or 5 years' time?
I'm going to need someone to repeat that question for me. The microphone in the room is not clear enough for me to have understood what was said.
Sorry, I'll give it another go without the face mask on. It's a question about infrastructure, two questions. The first one is the open storage network. What's the financial model that gives us an assurance about the longevity of the data that we might store there?
Yeah, no, there's none.
Okay, cool. It's cool to see.
No, so I distinguish between a analysis ready copy of the data and a primary data repository. So, when you've got downloaded data onto the server in your basement, what's your policy on the longevity of that data, right? Like, you don't have one. It's not a data facility. It is a personal copy of the data you're using for analysis. And that's kind of how we're thinking of cloud storage. It's not a primary data archive. It's not an archival quality copy of these data sets. It is a working copy of the data that we're using to collaborate. And I think if you start thinking about it that way, it creates a sort of different set of expectations around that data. So no, we can't promise to keep that data there forever. It's there for our team, for our collaborators to use and interact with. And if we don't need it anymore, or that it can't be sustained financially, then we'll delete it. It's kind of we're experimenting with this now. And so I think not having a 10-year preservation plan for everything on this architecture diagram is not a reason not to experiment with it.
Cool. And the second infrastructure question is about 2A2C, and in particular, access to resources which are under contention. So GPUs are more expensive than CPUs, and there seem to be fewer of them, and they're highly contended. So how does 2HDC handle that sort of access?
There's no contention in the cloud. There's an infinite amount of GPUs. So if you want a GPU, you just get one. Still has to be paid for, of course, but that's sort of a separate question.
Yeah, thank you very much for your presentation. One of the things my team is actually working on is how we could get all the data we're working on. We are still running below the gigabyte stage though. We are looking for how we could put all the data we're working on in probably structure like a database where everyone will have access to them to do analysis and what they do. Use them for the particular project they are working on, but there seems to be some tricky stuff coming up. So what do you think people that are starting to think about this kind of structure where they could collaborate over a certain group of data that will be useful to their project? What do you think will be the first step to actually building that database?
So I'm not sure I heard very well, but I think the question is like, what do we recommend to do for projects who like this idea of a sort of shared common data storage location that's accessible to computing for their projects? Is that have I understood it correctly?
Yes.
Yeah. So I think this is where we're seeing a lot of experimentation. I think in the UK, you're very lucky to have sort of the Jasmine and the CETA, computing infrastructure, because there's essentially one compute facility that is more or less accessible to the whole country, the entire research community in the UK. And so, if that existed in the US, maybe a lot of this wouldn't be necessary. But the fact is, in the US and collaborating internationally, we're a lot more fragmented. We've got DOE and we've got NCAR and we've got GFDL and all the universities, and there's no one computer we can all access. And so that's where we've turned to things like the cloud. Now, I think commercial cloud storage is a very viable option because it's accessible to computing, it's on the internet, and everyone can access it. The main blocker is that we just don't have a good way for projects to procure cloud storage, right? We're used to procuring equipment. We don't really have a good model. Our funding agencies don't really want us to, don't make it easy for us to buy cloud computing. That's why we're really excited about Open Storage Network, because it seems to be the sort of nice sort of intermediate solution. It's really on-premises storage that's compatible with both on-premises computing and cloud computing. So it's like a big object store in a rack. It costs like, I think $150,000, $200,000, and it has a couple petabytes worth of storage space, and just completely pre-configured. You just turn it on and plug it in, and you have that. So if your budget can, $100,000, $200,000, it's a lot, but in the scope of these big collaborations, it's not really prohibitive at all. It's less than the cost of a postdoc or something like that, right? So I'm really optimistic about Open Storage Network because it's coming in at the right price point and at a model, an equipment-based model that I feel like we know how to deal with in academia. So I would encourage you to reach out to them. There's, by the way, that effort is funded by Schmidt Futures, right? So if we in Vesri like this model, we can maybe take it up the food chain and talk to the Schmidt people and say, hey, this is our projects need something like this. It would be a nice synergy. I guess that was someone from Schmidt. Okay, great. Hi, Dan.
I just sent you an email.
Oh, okay, great.
So,
move into the shop on the other side of the room. So is there, if people were thinking about their hackathon project that they could do tomorrow, is there anything in Pangeo that would make a good project for someone to have a look at? Can you hear us, Rob? Can you hear us, Ryan?
Oh, I didn't realize it was a question for me. I thought it was something for the room. Sorry, but say again.
So if people were thinking about a hackathon project for tomorrow, is there anything in Pangeo that they could tackle? You mentioned at the end.
Oh, that's a great question. I would really encourage folks to have a look at XBATCHER. There's quite a few open issues. I think just putting it through its paces for some real world examples that you're working with would be useful. And the team working on it is very sort of open and welcoming to new contributors. So a great place to start with any sort of contributions in that space are just like documentation and examples, right? Like, you know, go through the documentation. Does it make sense? Like, do you understand what it's for? Can you, are there typos? Like, that's an easy entry point to start contributing to some of these tools. Then, like, does XBATCHER work for you? Like, what's your workflow? It's really designed to solve a problem that many of us have, right? I open my data set, NetCDF data set in XARRAY. Now I have to build a model and feed it through to PyTorch or whatever. So, you know, can we keep the XARRAY semantics without dropping down to just working with raw and NumPy arrays, right? And so I would point folks to that as a specific place to perhaps get started. I'll think if there's a more concrete project between now and tomorrow, and maybe send some ideas your way.
Okay, that sounds great. Thanks.